the program instructions, the program control instructions. We're talking about the unconditional jump. As we previously mentioned, instructions could be categorized into three different types, three different categories. The first of which is data movement instructions, instructions which are used to move a data from a place to a place, from, for example, a register to a memory location or vice versa, or bringing data in through some ports. So this is the first type of instructions. The second category is instructions which is called logical and arithmetic instructions. Instructions with which we do addition, subtractions, division, or multiplication for arithmetic instructions, or logically ANDing, ORing, XORing, NANDing, NORing if we're doing logical operations. The third type which we are discussing now is the program control instructions. We talked about the jump, and we have two types of jumps. We jump unconditionally or conditionally. In the unconditional jump, you don't check any condition to do the jump. You jump for the sake of jump. No condition is to be satisfied or met before you do your jump. Okay. So there are two basic conditions, two basic types or kinds of conditional jumps. Intra-segment jump, which is short or near, which means you do the jump within the already active code memory segment. You don't leave the currently active code memory segment to some other code memory segment. You stay inside your code memory segment. We call this intra, within the code memory segment. And inter-segment jump. Inter-segment jump means you're doing a far jump. You're going to leave the currently active code memory segment to another code memory segment to activate it and start executing a code written in this far code memory segment, in this new code memory segment. Inter-segment jump, again, it's meant to go to some new code memory segment. And the intra-segment, the jump within the the currently active code memory segment is done by modifying the value inside your IP. So you change the value inside your IP only. And it is divided into short and near. So when we modify the value inside your IP, we can modify it using 8-bit displacement, we call this short, or 16-bit displacement, we call it near. In both cases, short and near, you don't leave the currently active code memory segment to some other code memory segment. If you need to go to some other code memory segment, you do inter-segment jump, which means you have to modify both values, the value inside your CS and the value inside your IP. CS gives you the beginning, the starting effective address of your new code memory segment. IP gives where in this new code memory segment, where to start at, where to start executing a code. The machine code of this unconditional jump looks like this. If you're doing short jump, your displacement is only 8 bits. You provide only 8 bits, which means you may jump forwardly 127 bytes or backwardly 128 bytes. And the machine code is EB for this. To do near jump, you provide 16 bits to modify the value inside your IP. The opcode is E9. While the inter-segment jump, you have to provide a 32-bit operand, 16 bits for your IP, 16 other bits for your CS. And the opcode for this is EA, hexadecimal. Okay, again, your short jump may be as high as 127 bytes, and as low as 128 bytes. While your near jump, you are still staying in your code memory segment, and you are allowed to jump to forwardly to 32k bytes forwardly or 32k bytes backwardly, as high as 32k bytes and as low as 32k bytes. You jump upward 32k bytes and downward 32k bytes. So let's see an example of this unconditional jump. Jump 04. So this is a kind of short jump because the operand used is 8-bit operand. 04. This is an 8-bit operand, meaning you can jump through this operand 127 bytes upward or 128 bytes downward. We need only to jump 4 bytes upward. So these are the values of your CS and IP before execution. CS is 1000 hexadecimally, IP is 2 hexadecimally. So after execution of this jump instruction, your IP will be displaced 4 bytes or 4 places upwards. So if IP was 2, now it becomes 6. While your CS is still as is 1000, meaning you did not leave your code memory segment. Another type of jump is jump 20D hexadecimal. What this means is this: you are providing a 16-bit operand, so you need to do a near jump. Your jump becomes longer now. You can go upward up to 32k bytes or downward up to 32k bytes again. What this instruction does is this. Okay, your CS is this, your IP is this. Now, after executing this instruction, you don't modify the value, you don't add this 20D to your IP, you just replace whatever value inside your IP, which is 20B, by the new value given by this 16-bit operand. So your new IP would be 20D. See, we don't add it like the previous example. We just replace whatever value inside your IP by the given value of this 16-bit operand. Good. So this is another example for the unconditional jump. Now we are providing 32-bit operand. 32-bit operand. By this 32-bit operand, it means you need to go to a new code memory segment. A new code memory segment. This is why before execution we have this CS and IP, and this is after execution you place A3 00 in your CS, which means this is now a new code memory segment has been opened, and you start at this new code memory segment at this effective address, which is 127. So we modified both, we changed both the value inside your CS and the value inside your IP. Okay. Another example for the unconditional jump. You're given now the pointer bx, the base address pointer, within brackets, which means you are jumping to a place whose address is placed in bx. Well, when you go to your memory and point to a memory location by the value inside your bx, you go there. Do you get 8 bits and consider this a short jump, or you get 16 bits and you consider this a near jump, or you get 32 bits and consider this a far jump. The default is go there and get 16 bits. So what this instruction does, it takes you upward or downward by 127, 128, which means it does a short jump. So when you go to your memory, get 16 bits. Okay, good. So this is your value, your current value of CS, and the value inside your BX, and the effective starting address of your data memory signal. And this is the value of your IP. Good. You have to go to DS, get the value, which is 1000, multiplies it by 10, add to it whatever value written inside your BX. So when you add this, you get the physical address, which is 11,000. The third entry in your table, 11,000. So this is the lowest address. Okay. So you go there and get 16 bits. All the 16 bits, low and low and high and high, following little endian format. So you should place now in your IP 0002. This would be your new value of IP. This would be your new value of IP. 0, 0, 0 and 02. High and high, your higher byte is 02. It's here, 02. Low and low, your lower address value is 00. You place it in your lower byte of your IP. 0200. Good. The physical address of this new instruction to be executed is obtained now by multiplying CS by 10, add to it the value inside, the new value of your IP. So here are the 20 bits of your new physical address. Good. Another example of your unconditional jump. Jump, and the base address is filled with an effective address. But here we have preceded this by a double word pointer, which means when you go to the address pointed to by BX, you get double word, you get 32 bits, meaning this is an instruction to do far jump. You would have to modify both your CS and IP. Here are the values of your CS and IP. You checked your memory. This is the highest byte in your memory, 0A, and the next lower address is 10. So you take 0A10, place it in your CS, and instead of 0CDE, your CS will be now 0A10, which means you are trying to communicate with, to access a new code memory segment. And your new location to start executing at would be 0200. So you have to place 0200 inside your IP. So here are your new value of IP, which is 0200, your new value of your CS, which is 0A10. Good. So the conditional jump instruction, now we move to the second type of jump, which is conditional jump, meaning you do the jump after checking a condition. If the condition for the jump is satisfied, is met, you do the jump. Otherwise, you go to the next instruction to be executed. The next sequential instruction and start executing it. Here is the format for the conditional jump, the mnemonic code JCC. Then this requires an operand. So if the condition given by this JCCC is met, you jump to a place determined by this operand. And remember that all conditional jumps are short jumps. So you're not allowed to do conditional jump and go outside the code memory segment or even do a near jump. You're allowed only to jump as many as 127 bytes forwardly and as many as 128 bytes backwardly. Okay, this is the range of your jump, plus 127 bytes to minus 128 bytes. Good. So we have a long list of conditional jump. For example here, JC, what does this instruction do is this. You do the jump after checking the condition of your carry flag bit. If your carry flag bit is 1, you do the jump. Otherwise, you go for the next sequential instruction and start executing from there. Start running your program from there. Alright, for example, here is another syntax of your conditional jump. Jump not equal, which is totally equivalent to jump not 0. So if the two numbers under considerations are not equal, which means the 0 flag bit is not set, indicating that the difference is not a 0. 0 flag bit is a 0. Alright? So if the two numbers are not equal, which means the difference is not 0, you do the jump. Otherwise, you go to the next instruction, the next sequential instruction, and start running your program from there. Good. Let's trace this program. Okay, compare AX to BX. This compare instruction, what it does is this. It calculates the difference, AX minus BX. So it's sort of a subtraction. But the result of this subtraction is not saved, is not stored anywhere in your memory or register. The value of this result, AX minus BX, is only taken to affect the flag bits. Which means what? Which means this. If your BX was larger than AX, it means to perform this subtraction, you will definitely need a borrow. So what CMP, what compare instruction does, is to set the carry flag bit. When the carry flag bit is set, it means a borrow was needed, which means your BX is greater than AX. Otherwise, if AX is greater, you did not need a borrow to perform the subtraction, and your carry flag bit will not be set. If you check your carry flag bit, you'll find a 0 there. So a 0 carry flag bit indicates that AX is greater than BX. A 1 in the carry flag bit will indicate that BX is greater than AX. Good. So you jump below. If AX is lower than BX, okay, AX is lower than BX, you will need a borrow and your carry flag bit would be set. So what this instruction JB does is this. It checks for the carry flag bit. If it's set, if it contains a 1, it does this jump to def2. Otherwise, it will go and move the value from the register AX to DX. Okay? But if the carry flag bit was set, indicating that your BX is greater than AX, it goes to def2. And def2 does this. It takes bx, which is the larger value, place it into dx, all right? Then subtract ax from whatever value that was placed in dx, which is bx. So get now the difference between ax and bx. If bx is larger, it's a positive difference. Place it in dx. With sub will subtract ax from bx, and the result is placed in your dx. Okay, then you're done. All right. Otherwise, if your ax was greater than bx, you don't do this jump, all right, and you start at the next sequential instruction. You again move ax to dx, then subtract bx from dx, and place the result in dx. All right. So all this means you check ax versus bx. If ax is larger, calculate the difference ax minus bx and save the result in dx. If bx was the larger, calculate bx minus ax and save the result into dx. So we're saving the absolute difference between ax and bx in dx register. So here you are. If ax is larger, you get ax minus bx and save it in dx. If ax was smaller than bx, you get bx minus ax, place the result in dx. Good. Let's trace another program. Now, this instruction is saying what? What this instruction is trying to do? Well, it takes the effective address or the offset of an array named table and place it into di. So now di points to the first entry of an array named table. How many elements does this array contain? We don't know yet. What are we trying to do? We'll see when we scan the rest of the program or trace the rest of the program. But at least now we know that this instruction makes di to point to the first entry of an array named table. Well, we're placing 100 in cx. It seems that we're going to do something 100 times because cx is our counter now. All right, good. Load your AL with 0A. We're placing 0A in AL. Clear the direction flag bit, which means what? Starting from an entry, you are going to go upward to check the second, third, and fourth, meaning you're going to increment our index di, not to decrement, because we're clearing the direction flag bit. If the direction flag bit is cleared, you place a 0 in there. This indicates you're going to move forwardly within your array or block of data. Good. Here, what we're trying to do is this. We are going to repeat of not equal. Repeating what we're scanning these 100 elements. We check every element we read against 0A. All right. So this is scan string byte by byte. This instructions is repeated if every byte to be scanned, to be checked against 0A is not equal to 0A. So it seems that we have a table or an array of 100 elements, and we are trying to check every element starting from the very beginning against 0A. Okay, and we are going to repeat this. If we don't find 0A within these 100 elements, we are going to repeat it. So if the first element is not equal to 0a, we go to the second element. If the second element is not equal to 0a, we go to the third element, and we do this scanning till what? Till Cx is 0. If we scanned the total 100 elements in this table and we never found 0a inside, we have to jump and say we did not find this. Jump if Cx, this is what this instruction means. It tells your program to jump if Cx is 0 and jump to a label saying not found. We did not find a 0a value within these 100 elements. Good. So this program scans a table of 100 bytes for a value of 0a. Now we go to a very important instruction with which we can control the flow of our program, the flow of our execution, which is the loop instructions. In many incidents, we need to go over a piece of code many times. All right, when we're solving any problem, we will at some time require a piece of code to be repeated many times. We call this looping. Okay. And at the jump, we do have two different types of looping. We can loop, go over some piece of code many times, or do this, we call each time is an iteration. We do as many iterations as you wish without checking any condition. You may as well go over a piece of code many times as long as a condition is met. So this is the difference between unconditional looping, no condition to be checked to loop, and conditional loop, you have to check a condition. If it's satisfied, you go and you do one more loop or one more iteration till the condition is not met. You go outside the loop. All right. How many times you need your code to loop before getting out? Either a condition is met to take you out, or the number placed in Cx becomes a 0. So your unconditional jump, your unconditional looping looks like unconditional jump, and at the same time it's checking the value inside Cx. So you loop unconditionally a certain number of times. This number of times is placed in